So my name is Kentaro Shikata from Mitsubishi Heavy Industries Research Department. So thank you for giving us the great opportunity to present a case study on the optimization value chain with using the newly implemented transport class in PLEXOS Universal model. So before talking about the simulation, so let me briefly introduce what we are. So Mitsubishi Heavy Industries, so MHI, provides various wide range of products and services such as high efficiency power plants, CO2 capture plant, and ships and so on. So and for about the past 10 years, so we have been using the PLEXOS for evaluating the market value of our products and services in various industrial fields. And MHI have set a target called Mission Net Zero, aiming to achieve the carbon neutrality, including the Scope 3 by 2040. But to achieve such aggressive target, so we believe that it is essential to expand the use of the CCUS as well as to promote the energy transition to the clean hydrogen or ammonia across the various industrial fields. To support the expansion of the CCUS, so we are developing and commercializing the key technologies across the CO2 value chain, including CO2 capture, storage, transport, and utilization. So in particular, we have the world's leading track record in post-combustion CO2 capture from exhaust gas, and we have also studied the demonstration of the liquefied CO2 carriers. In the future, so we aim to provide the integrated total solutions by combining these technologies. And in Japan, so efforts are underway to establish the CO2 value chain through the Advanced CCS project supported by METI and JOGMEC. There are 9 projects in Japan, and some projects are considering the CO2 transport via domestic pipelines, while others are exploring the ship-based transport, both domestically and internationally. MHI is supplying the equipment to all those projects and is also participating in one of them here, so in the north area of Japan. However, but many of these projects are facing challenges in establishing the clear pathway to economic self-sufficiency. So to overcome this challenge, we believe that system-level optimization, assuming the future expansion of the value chain, is essential. So in the early stage, so project design and investment planning are typically carried out among the limited number of the stakeholders. As a result, it is often difficult to find the opportunity or room for cost reduction. However, as the value chain expands, by integrating the multiple stakeholders and off-takers and optimizing the entire system, we can create a synergy. This can promote the infrastructure standardization and shared utilization, leading to further cost reduction. To address this need, we collaborate with Energy Exemplar team, so Robson team, so to develop a new transport model within the PLEXOS Universal model. In the following, I will introduce the case studies using these new features, which has been available since the latest version, so version 12. As many of you may already know, the transport class itself has been implemented in the gas model. But the new transport class further enhances the flexibility particularly in selecting the loading points, unloading points, and the transport routes. It enables the optimization of transport problems in complex value chains involving the multiple suppliers and off-takers. In addition, so latest update supports stochastic optimization, so allowing better decision-making under uncertainty. So from here, I will introduce 2 case studies using this transport class. So first, case study on CO2 value chain in Japan. So this figure shows a simplified overview of the model. So in case 1, so emitter O1 is paired with off-taker A1, and emitter O2 is paired with off-taker A2. And each pair independently optimizes facility configuration and operation of the all equipment for CO2 capture, storage, and transport to minimize the total cost for meeting the off-taker's demand. But in case 2, we assume that transport vessels as well as port facilities and onshore tank at the off-taker side shared between the off-taker A1 and A2. And in case 3, so we further assume that the emitters O1 and O2 share the onshore storage tanks and port facilities at the location O, like that. And emitter O1 and O2 represent the different types of the businesses. So resulting in different they have the different CO2 emission profiles. So O1 represents power generation facilities. So with higher CO2 capture during the summer in Japan from this time. So Japan has an opposite season in Australia. So, and O2 represents a district heating system with higher CO2 capture from January to April during this season. So in addition, the O1 has a larger annual CO2 capture potential than the O2. So next, let me explain the configuration of the new transport model. So this model allows us to define the transport capacity, travel time between each location, and loading time and unloading times. So we can also define the multiple candidate transport routes and assign the costs to each route, such as fuel cost or port fee. So based on these settings, the model evaluates which routes should be selected and optimize the overall transport process. So in case 1, each vessel do the shuttle transport between the O1 and A1 or O2 and A2. But in case 2, so when the vessel leaves the location A, they always choose a return point, so which point with considering the CO2 emission profile and the stored amount of the CO2 in the onshore tank to minimize the total cost. And furthermore, the model supports the LT plan as well. So by including the capital and the fixed O&M cost, we can optimize the decisions such as the number of the vessels to be installed or the selection of the vessel types. To represent the flow of the CO2 value chain, we model the facilities such as the CO2 capture units, liquefaction plants, storage tanks, and pipeline using the process class and facility class in universal model as well. So for all facilities, we define the operational constraint, CapEx, and OpEx. So based on these inputs, the model derives the optimal facility configuration and the operation patterns of all facilities that satisfy the CO2 demand at a minimum cost. And this slide visualizes the vessel operation in each case. So in case one, so upper graph, so the two vessels are installed between the O1 and the A1. And one vessel between the, is installed between the O2 and the A2. So red and blue line represent the shuttle transport between the O1 and the A1. And the green line represents the transport operation between the O2 and the A2. And when the colored line reaches the solid line, so that means the vessel, vessel is loading or unloading at each point. But sometimes, so the colored line is stayed on the dotted line. So that means the vessel waiting offshore near the port. So as you can see, during the high CO2 emission periods, each vessel can operate almost continuously. But during the low emission season, so we can see the long dwelling time. So it's a waiting time of the vessel in case one. But in case two, so by sharing the vessels, so either ships can support the transport from the other emitters like that. So this reduces the number of vessels and decreases the dwelling time. In case three, so by further sharing storage tanks and port facilities at the emitter side, so emission profiles are smooth. And this reduces the storage requirement capacity and improves the operational efficiency of the vessels. This slide presents the result of the transport process and the installed facilities. The upper table shows the amount of the CO2 transported to the off-takers, as well as the summary of the operation of each vessel. In case one, so most of the captured CO2 can be transported to the off-taker, but we can see the long dwelling time for each vessel here. As we move to the case two and case three, so vessel utilization becomes more efficient by sharing the facilities, and total amount of CO2 transported to the off-taker increases. The lower table shows the number of the vessels and the installed capacity of the onshore tank. With infrastructure sharing, emission profiles are smooth, reducing the excessive capacity and avoiding the overinvestment. Then, so this graph shows the levelized cost of CO2 across each cases. So with case one normalized to be one. By sharing infrastructure, so CapEx and fixed O&M cost reduced. As a result, the levelized cost of CO2 in case three is reduced by 26%, like that. So next, let us consider the similar problem in the different context. So in this second study, so we assume the green ammonia is produced in India and Australia and transported to Singapore for power generation. So as you may know, India and Australia are aiming to expose the clean hydrogen or ammonia by utilizing their abundant renewable energy potential. And also, Singapore is considering the usage of the green energy, so for their power generation or bunkering, so industry for decarbonization. This page shows the characteristics of renewable energy in India and Australia. So as you can see, in India, the wind power generation, so green bar, significantly increased during the monsoon season from the May to September. In contrast, in Australia, solar power generation, so orange bar, increases from September to February. It's a summer season in Australia. So in other words, the seasonal patterns of renewable energy availability are complementary between the two countries. So when we connect each countries by the transport class and optimize the ammonia production and evaluate the levelized cost of electricity in Singapore, the result is shown on this page. The upper graph shows the monthly ammonia production in India and Australia. And the monthly average ammonia production in each country is normalized to 1.0. And the lower graph shows the levelized cost of electricity when this ammonia is used for power generation in Singapore. So left two graphs, so if ammonia is sourced from only one country, India or Australia, so production fluctuation depending on the renewable energy availability in that countries. However, by sharing the transport vessels and sourcing ammonia from both countries, these fluctuations can be balanced. As a result, ammonia production becomes more stable, and this allows us to reduce the required capacity of renewable energy, electrolyzer, and storage tanks, while also improving the transport efficiency. As a result, the levelized cost of the electricity is reduced by 13.5% compared with the Australian case and the Indian case. So this example demonstrates that optimizing transportation and integrating multiple supply sources can create some value on the ammonia value chain as well. So that's a conclusion, my summary of my presentation. But optimizing the entire value chain, including the transport process, allows us to identify the synergistic combination of the stakeholders and quantitatively evaluate their benefits. So through such analysis, we aim to support the expansion and the realization of value chains in the world. So that's all my presentation. Thank you very much for your attention.